Cauchy was the first mathematician to write a rigorous calculus text. The famous and widely recognized functional equation shown on screen appeared in his 1821 landmark textbook entitled Cours d'analyse de l'École Royale Polytechnique. Cauchy solved the functional equation to find all continuous functions which satisfy it. The equation is now known as Cauchy's functional equation, or more precisely Cauchy's first functional equation. The reason for calling it first is that Cauchy introduced not just one, but 4 functional equations. Alternative names encountered for the equation are Cauchy's linear or Cauchy's additive equation. Since the time Cauchy wrote it down, the functional equation has proven to be one of the most important equations with applications in many areas in mathematics and sciences. Furthermore, using various mathematical tools, many other functional equations can be solved by transforming them into Cauchy's equation. I will present the solution of Cauchy's equation using the ZQR method, which can be used for many functional equations. The name of the method was introduced by mathematician Costas Efthimiou in his book, Introduction to Functional Equations, and it is based on the fact that the method solves the equations in 3 stages. In the first stage, the equation is solved for the integer numbers. In the second stage, the equation is solved for the rational numbers. And finally, in the third stage, the equation is solved for all real numbers. As a quick comment, it should be mentioned that Efthimiou called the method NQR and not ZQR, since often the domain of the function may not include negative numbers. However, in this case, the domain includes the entire set of real numbers, and hence I opted for ZQR. The passage from the second to the third stage makes use of 2 important results. The first result is that any real number can be represented as the limit of a sequence of rational numbers. The second result is that the continuity of a function allows the exchange of the limit and the operation of the function. We are ready now to work out the solution of Cauchy's equation. First, we will rewrite the given equation to include any number of arguments. The modified equation will be used to find a result for integers and rational numbers. Hence, in the defining equation, we set x1 for x and x2 plus x3 for y. This results in a similar functional equation, but for 3 arguments. We can repeat this process to get an equation for 4 arguments, and an equation for 5 arguments, and so on for any number of arguments. Now in equation 2, we set all arguments equal to 1 to find that the value of the function at n is n times its value at 1. Let's set the value of f at 1 equal to c, with c being an arbitrary real number which cannot be determined. Then the value of the function at any natural number n is c times n. Setting x and y equal to 0 in the original equation, we can easily see that the value of f at 0 must vanish. Then, setting minus x for y in the original equation, we see that f is odd. This implies that the result found for the natural numbers is true for all integers. Returning to equation 2, now we set all arguments equal to the fraction m over n, where n cannot be 0. The resulting equation shows that the value of f at the fraction m over n is equal to c times the fraction. Therefore, the function f of x has the form c times x for any x that is a rational number. If x is a real number, let's represent it as the limit of a sequence Qn of rational numbers. Then, the value of the function for any member of the sequence is c times that member. In the limit of n to infinity, the continuity of the function allows to exchange the limit with the function and find that f of x is c times x. Conversely, any function of the form c times x satisfies Cauchy's first functional equation. Therefore, we have proven that if the function f is required to be continuous, Cauchy's first functional equation is solved the functions of the form c times x, and only them. Darboux was the first to realize that Cauchy's equation leads to the same solutions if the requirement of continuity of the function at all points is dropped and some other weaker condition is added. In particular, Darboux proved that, given Cauchy's first functional equation, if f is continuous at a single point, then it is continuous at all points. Some other conditions that can replace the continuity of the function at all points are 1. The function is increasing for all non-negative numbers. 2. The function is monotone on any interval. 3. The function is bounded above on any interval. 4. The function is Lebesgue measurable. 5. The graph of the function is not dense in R2. However, if no additional condition is given, Cauchy's equation admits way more solutions, which are currently excluded by continuity. In a follow-up video, I will show you how to solve the equation without any additional conditions. I hope you liked this video. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.